Good evening, everyone. I welcome you to the 11th problem solving session of combinatorics course. So, today we'll be discussing few problems on Burnside lemma and bit of species. So, let's start. So, last time we were kind of counting an orbit. So, last time we saw that we had a set Y, a group was acting on that set Y, and we were interested in counting the number of orbits. So Burnside lemma helps us in doing that. So what does Burnside lemma say? That suppose we are given a finite set Y, and suppose G is a subgroup of group of permutations on Y. So it is so we can see we have a group, we have a finite set, and then we have some group acting on Y, and giving a group action is equivalent to giving a subgroup of group of permutations in Y. Because if you want to give a group action on Y, it is equivalently we can assign a permutation of Y to each G. So we are given a finite set Y, and G is a subgroup of group of permutations, and then G mod Y we are denoting as the set of orbits. Then Burnside lemma says that number of orbits is equal to 1 upon mod G, that which is the order of the group, and we take the sum of fixed elements of pi, and pi varies over phi varies over G. So in other words, Burnside lemma is saying that number of orbits in a group action, if a number of orbits in a group action is same as the average elements fixed by a permutation. So this was the Burnside lemma. Then we had a nice application of this Burnside lemma to count non-equivalent G colorings, which is as follows. So we have the same setup. We have a set X, and then we have a G, which is a subgroup of symmetries of X. But now here we also have an additional information. We also have a set of some colors, and order C is equal to NC. So now a coloring on a set X is a function. It is a function from X to C. So coloring on a set X means that we are assigning a color to each element of X. Now two colorings, we say that two. So we have a set X, and then we have a subgroup of symmetries of X. So we have some symmetries of X. So now two colorings, two functions from X to C will be called G equivalent if f can be obtained from G after doing one of the symmetries in the group G. So in other words, we are saying that two colorings F and G are equivalent if there exists a pi belonging to G, that is a symmetry in G such that F composed with pi is same as G. So this is basically saying we can achieve two colorings are equivalent if we can achieve the second coloring by one of the symmetries of X from the group G. So now we want number of, if we want to count the number of G in inequivalent coloring on X, they are just 1 mod G. Okay, this is not equal to number of inequivalent G inequivalent colorings on X are given by 1 mod G sum of NC pi. Pi belongs to G. Here N is the number of colors and C pi is the number of disjoint cycles in pi. So any permutation pi can be written as a product of disjoint cycles, and number of disjoint cycles in pi is we have C pi. So this is the application. Now once we have recalled the statement of Burnside lemma and its application, let's solve some question. So our first question is this. So we have 15 balls which have been put up in a triangular array as in the figure below. So in this figure we have these 25 balls which have been arranged in a symmetric manner. So we have a so this figure might not be symmetric, but because I have drawn it, so it's a bit messy, but in actual what we have, these are placed in a very symmetric manner. So if you see, so we have these in a way there we have these two little triangles. So we are placed and these dots or vertices are denoting the center of the circle, and all the circles are symmetric, all the circles have same radius. So in the bigger triangle we have 12 circles, and in the inner triangle we have 3 more circles. So 15 balls or circles have been arranged in this triangular array, and we have to find we want to find the number of different arrays which can be made with 3 distinct colors if array is free to rotate. So we have to count we have to count the number of different arrays that we can obtain, and since it is an array, so if we rotate it, it remains the same figure, right? It remains the same object. So we have to find find basically G inequivalent Kerr rings where order C. So now if you want to, so from our previous setup, what is our, so we have that order C is 3. What is G? We have our array is free to rotate, so G is the group of rotations on triangular array. And what is our X? X is basically these 15 balls. So the number is denoting the ball. Now we want to find G, number of G inequivalent coloring. So we can see this is a triangle. So the rotations, so what all rotations that we can do so that we obtain the same figure is basically we can rotate by 0 degree, which is just the identity, or we can rotate it by 120 degree, or we can rotate it by R240. So now we want to find the number of sorry yeah, so I need this picture. Okay. So yeah, so what do we want to find? We want to find the G equivalent curling, and from our application to Burnside lemma, we know that the number of G inequivalent coloring so we are discussing this question. So we have 15 balls which are put in a triangular array as in the figure below. So we have these 15 balls which are arranged very symmetrically. So in the bigger triangle they have been 12 balls have been arranged, and in the inner triangle we have 3 more balls. So we have these 15 balls which are arranged in such a manner, and we have to find the number of different arrays which can be made with 3 distinct color if array is free to rotate. So we have Uh, so we have to find the distinct arrays that we can find. So this we'll solve using the application of Burnside lemma. So Burnside lemma. So what is our data given? So we have the number of colors is 3. Number of group G, the symmetry and number first set X is these 15 balls 1 to 15, and G is the so array. So we are saying two arrays are same if the two colorings are same, if they can be, if one can be attained from other by a rotation. So G is the group of rotations on this triangular array. And now we want to find G inequivalent coloring. So first of all, what is our group G? It is group of rotation. So what all rotations are possible in triangle, such that if we are rotating, taking this as center, what all degrees are possible, so that after rotating we get the same figure. So we have 3 rotation, which is R0, R120 and R240. So now we want to find the so now we want to find the number of G inequivalent coloring, and this by application of Burnside lemma is same as we take 1 over order G, pi belongs to G, and we take n C pi. So here in our case order G is 3 and n is also 3. Now we have to find C pi for each of these. So first of all, what R0? This is the identity rotation. And if we have 15 balls, we see R0 is basically fixing each of the balls. So position of none of the balls is changed. So R0 is the identity transformation, and number of disjoint cycles in R0 is number of disjoint cycle in R0 is 15. So we see so number of cycles are 50. Now the second is R. Now the second rotation is R to 120. So can you so what is R to 120 doing? So we are rotating by 120 degrees. So we see that if we'll rotate by 120 degree, 1 will go to 5. So we are rotating this figure by 120 degrees. So we'll see that 1 will go to 5, 5 will go to 9, and 9 will go to 1. And similarly, this second, so these 3 balls will be changed. So we'll have this. After rotating by 120 degree, 1 will go here, 5 will go here, 9 will go here. Now now this 2, so 1, 2, 3, rotating by this edge is this edge. So now this is 1, 2, 3, 4, 5. Now this edge is becoming this edge after rotating by 120 degree. So this is 6, 7, 8, 9, and now this edge is becoming this edge. So this is 9, 10, 11, 12. So is this fine? And similarly the inside balls. So 13th ball go here, 14th ball here, and 15. So after rotation by 120 degree, our figure is like this. So, and if we want to write it as disjoint, if we want to write R120 as product of disjoint cycle, it will be 1 goes to 5, 5 goes to 9, and 9 again goes to 1. So the cycle is closed. Now we look at 2. 2 goes to 20. 2 goes to this is 9. This is 10. This is 10. So 2 goes to 10. 2 goes to 10. And where is 10 going? 10 goes to 6. And where is 6 going? 6 goes to 2. So this cycle is again closed. And similarly for others, we see 3 will go to 7. 7 is going to 7 is going, okay, 3 3 is going to 11. Sorry, 3 is going to 11. 11 goes to 3 is going to 11. 11 goes to 7. So we have 3, 11, 7. And here also we have 1 goes to, this is 1, 9, 5. Oh, sorry. 2, 10, 6, 3, 11, 7. And this is, now we have 4. 4 goes to 12. 12 goes to 8. And 8 is again going to 4. And then the rest, then we have these 13 goes to 15 and 4. And R240 will be just the inverse of this. So inverse of this will be 1, 5, 9, 2, 6, 10. That is we rotate it once more by 120 degree, or we rotate the original figure by 240 degrees. 7, 11, 4, 8, 12, 13, 14. So here the number of cycles are, we see 1, 2, 3, 4, 5. So C R120 is 5 and C 240 is also 5. So we see that by application of Burnside lemma we get that this number of G inequivalent curling is nothing but 1 by 3. Now 3 raised to the power 15 plus 3 raised to the power 5 plus 3 raised to the power 5. So this is the answer. So is this clear? Is the first question clear? Shashikant? Okay. Am I audible? Okay. So this was the first question. So this was when we applied the application of Burnside lemma. Alternatively, if we wanted to do this directly by Burnside lemma, let's do it directly by Burnside's lemma. So Burnside lemma says that number okay, so 1 over order G, and this is pi belongs to G, fixed pi, and our set Y is colorings on triangular array. So we see first is the so the set is basically this, and group action on any coloring. So any coloring here is a function from f is a function from number of all the balls to the 3 colors, say red, blue, green. So set Y is basically the collection of Set Y is basically the collection of all the colorings on triangular array, and the group action is that, so if we want to say G belonging to G, if G is acting on F, so G dot F is another coloring in Y. And how is it defined? G dot F, take any A to F applied to G dot A. So our group is the coloring on this triangular set of colorings on this triangular array, and the group action is group. So another, so if we are applying pi to some coloring, so what we are doing, we are rotating, we are rotating, first rotating it, and then the coloring. So now if we want to find fix R naught, so R naught is the identity permutation. So R naught is the identity permutation, and so all the colorings will be fixed by R naught. So we see that order of fix R naught is 3 raised to the power 15. This is, all the colorings are fixed by R naught. And how many colorings are there? So we have 15 balls. Each ball has 3 options. So the total number of colorings are 3 raised to the power 15. So fix R naught is 3 raised to the power 15, and fix R 120. Order of fix R 120. So if we have some coloring which is fixed by R 120, so what is R 120 doing? R 120 is sending the first ball to the fifth ball to the ninth ball, and ninth ball to the first ball. And similarly, it is sending second ball to the fourth ball, second ball to the sixth ball to the 10 ball. So we see that these five partitions, these are the 5 partitions of R120, and each of these partition should get the same color, because if two colorings are fixed by R20, that means color of 1 should be same as color of 9, and color of 9 should be same as color of 5. So all these 3 balls should receive same color. Similarly, the next 3 balls also should receive same color. So we have that. So we have these. So each of these 5 set should receive the same color. So we see that fix R120, order of fix R120 is 3, 5, and order of fix R240 with similar logic will be 3 raised to the power 5. So we see we are now if we are applying the Burnside lemma also, then also we are achieving the same thing as we should. So is the first question clear by both the methods? Preeti and Shashikant, am I audible? Okay. So now next question. Next question is that we have been H is the given graph here. So we have this graph with 8 vertices, and these are the edges, and we have to find the number of ways to color the edges of H using 3 colors, where 2 colorings we are saying are identical. If H has an automorphism that takes first coloring to the second one. So now here our set Y. So here our set Y is the edges of graph H. So we have these vertices 1, 2, 3, let me name them, 4, 5, 6, 7, 8. And set Y is the edges of graph H. So all these edges A, B, C, D, E, F, G, H. So So, and two colorings, we are saying two colorings are same if two colorings are same if H has an automorphism that take first coloring to the second one. So first of all, H is a graph. So what do we mean by a graph isomorphism, graph automorphism? So we need, by graph or automorphism, we mean a map sigma from the vertices of H to the vertices of H such that sigma is a bijection. Moreover, not any function won't work. The other since it is a graph automorphism, and graph has two sets. It has a set of vertices, it has a set of edges. So first to define a graph automorphism, first we need a map from vertices of H to vertices of H, and secondly we want that if v1 v2 is an edge, that is edge should go to an edge. So if v1 v2 is an edge, sigma v1 and sigma v2 should also be an edge. So if we can set up a bijection, should be an edge. So if we can set up a bijection between vertices in such a manner such that whenever v1 v2 is an edge, sigma v1 v2 is also an edge, and this will give us an automorphism of H. So now we are saying that two colorings on this set of edges are same if one coloring can be obtained by other via this automorphism. So now it is easy to check first of all that or any graph automorphism.
I have a question.
Yes. Yeah.
How many sessions will still remaining? I mean,
Okay, this is the second last session. Will be one more session after this.
okay. Will there any revision session kind of before the examination?
I'm not sure about that. Okay, like okay.
I mean, like just before the in a previous week of before examination, if
Okay,
you can
when is
have
your exam?
it's perhaps 29th or 30th.
Okay, okay. So like we there will be a session next week. So we like if you have some problems, you could post in the session. Like we can discuss
Yeah,
that in
yeah.
the
I
next
mean,
session.
I'm actually,
Hmm?
I'm just laid back in this course, so
Okay.
I fear that I'm not be capable of completing the whole syllabus within next week. So
Okay. Okay.
I mean,
Yeah.
if it's possible for you, you can take an extra session just before examination.
Okay. On what topic you want the session?
I mean, for whole syllabus, whatever, I mean, confusion or
Okay. 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 I will look into it. Okay.
Okay, thank you.
Yeah. Okay. So now it is now you can check that this check that graph automorphism preserves degrees. So by a graph automorphism I mean that we have to set a map between the set of vertices, and since we have this so since it is a graph automorphism, it is in a way we are saying that we have the same collection of vertices and edges. So it is logical to think that if it is a graph automorphism, it will be preserving degree of vertices. By that means if a vertex v1 has degree d, then sigma v1 will also have degree d. So now in this question, now in this question we see the vertex 1 has degree, so vertex 1 has degree 2, vertex 3 this has degree 5, vertex 2 has degree 4 and all other vertices have degree 1. So if we have to set up a bijection, if we have to set up a automorphism, first we are trying to calculate the group of, so we are trying to calculate group graph morphisms of H. Since, and we have seen that degree of, so if we look at these V1 vertices and then their degree V1, V2, V3, V4, V5, V6, V7, V8. So we saw that in this graph. Okay. So this is this graph basically. One, two, three. 4, 5, 6, 4. 4, 5, 6, 7. Okay, Shashikant. So are you able to understand today's session? If you want to discuss, like if you want to discuss any, like I'll continue with this, but if you want to specifically discuss some previous assignment or some previous problem, we can discuss that also. Or should I continue with this only? Preeti, you can also say, like if you want me to discuss some. Yeah.
Yes, ma'am. I have one question, and that's why I joined here, ma'am.
Yeah, sure.
Actually, ma'am, this question is related from set theory.
Okay. Yeah.
Ma'am, I have some finite sets. I'm just telling you a question.
Yeah.
So I want to find the minimum collection of subsets whose union will be set of all elements.
Okay.
Then minimum subset.
Okay.
Then, ma'am, how can
Yeah.
find?
Okay. So you have a. Can you repeat your question? So you have a set.
Yeah, you have a finite set.
Okay, we have a finite set. Yeah.
Yeah, and some collection of subsets.
Okay, some
If
collection
it's
of.
subset, then yeah, a size is fixed. Subset size is fixed. Suppose 3 size, 4 size, but here size is fixed. So
Size of subsets or the number of
it's
subsets?
fixed. No, size of subset is fixed.
Okay, size of subsets is fixed.
Suppose length 3, 4, this type. If we take 3 size, then all subset is 3 size.
Okay.
And if we 4 size, then all subset will be size 4. Then we want to find the minimum number of collection of subsets.
Fine.
Whose union is whose union gives all element of sets.
Okay, find minimum number of collection of subsets
whose union will be all set.
Okay. Union.
Then ma'am, just how can find?
Yeah, let me think. Wait. So you suppose you have a finite set A, A1,
yes,
AN. Suppose it has n
yes,
element, and
G.
and this size of subset is K, right?
Okay. Yes, ma'am. Yes, ma'am.
Okay. So now.
Ma'am, we are taking collection of subset with size k.
Yeah. Size of subset is k. Yeah.
Yeah,
Each of the subset has uh, each
size k
thing. Yeah. Okay. Now you have to find minimum number of collection of subset whose
whose
union will be A.
a set. Yeah, a. Yes, ma'am.
So okay, so I think what you mean is that so you want to find the minimum number.
Yeah,
So
minimum
is
number.
it like, is the question is this, so like you want to find the minimum number, like suppose the minimum number is, suppose the answer is, suppose the answer is say m, then we are saying that if we pick, if we pick any m sets, any
Yeah,
m
m.
distinct sets,
Yes, ma'am.
then their union should be the whole set, right?
Whole set. Yes, ma'am.
Okay, okay. A1, if we pick any m distinct sets, and this
And
and for any, so by minimum number you mean this only, na, that if the answer is m, then any m, any then any then any collection of k subsets with size
yes,
m, it
yes,
will be
ma'am.
true for any collection. No, you don't just need
Yes,
one collection, right? It should be true for all these collections of the size m. Oh,
yes, ma'am.
okay. Okay, let's see how we'll do this. So
And
uh,
ma'am, one thing is here also,
yeah.
uh, where if you take two subset, then
Hmm.
intersection not equal to 5.
Okay, wait. So this is another question you are saying, or like
No, ma'am, including in this question.
in this question only? Or so?
Uh,
Acha,
intersection of two subset not
hmm.
equal to 5.
So they should be pairwise disjoint. All sets. So there should be two sets.
Intersection not equal to 5. If
Oh,
you two take sets,
hmm.
then intersection not equal to 5.
Okay. So you mean okay? So they are so for each pair you are saying that their intersection should not. So they should not be disjoint. You mean
Yes, ma'am. Yes, ma'am.
each of them?
Yeah, each of
Each
them.
each of the pair is, but that is not possible, right? Or is it possible?
Yeah, ma'am, it is possible.
Uh, each in this question, okay. So for I understood this part, that we want to find the minimum number of collection whose union will be A, and this
Yeah.
collection you are saying uh, any two sets here should, their intersection should not be empty.
Yes, ma'am.
Okay, so first let's see, like if we can find, like we'll look at that condition also. First let's see if we can find the minimum number of collection whose union will
Yes.
be A. Okay.
Yes, yes, ma'am.
uh okay, so suppose the size is k.
Yes, ma'am. Suppose the size is case.
So
Okay, ma'am.
hmm, okay, so if k was 1, then your m is trivial, it should be n, right?
Yes, ma'am. Yes, ma'am.
Now if your k is 2,
2.
now if your k is 2, then by pigeonhole principle or something, we can maybe use pigeonhole principle. Let's see if we can.
Yes, ma'am. We can. I have also used, ma'am.
Yes, okay, what you have done, yeah, like, yeah, you can tell if you want.
Yes, ma'am. I got, ma'am. I got answer. Selling function mm, n upon e upon k.
M is
M is equal to selling function
ceiling function.
e upon selling. You are writing, ma'am, floor.
Okay,
Selling function.
slow. Okay, so okay,
Selling function e upon k.
n upon k.
E. You are taking a, na, ma'am.
A, what is A?
Yeah,
A.
you are taking capital A, na, ma'am.
Yeah, capital A is a set,
Yeah, set.
so
Then
it has
E
n
upon K.
elements, so n over k, right?
Yes, ma'am.
Yeah, so okay, so you are getting this.
This, ma'am. Yes, ma'am.
So here is okay.
Yeah, ma'am. I got the answer, but how can proof, ma'am?
Okay,
Can
so
you,
first, okay, so how did you get this as the answer, as in
ma'am, through pigeonhole principle, ma'am.
pigeonhole principle? Okay, so see, okay, wait, yeah, so if your k is 2, if your k is 2, m is n, So here, like, it will be n by 2, you mean the ceiling function
Yes.
of n by 2.
Yes, ma'am.
Okay, because if we have ceiling function of n by 2, so is it like, I want to see, like, wait, if my n was suppose 4,
Two. Yes, ma'am. Suppose four, then
a1, a4, then you are saying any,
size. If you take size two,
and okay, if you are saying n by, yeah,
k
oh,
equal to two.
okay, uh okay, k equal to 2, n equal to 4 and k equal to 2, then any
Two.
two subsets should give you. But no, right? So a1, see, if I consider these two sets, a1 a2, a1
Eight.
a3,
Yes,
the
ma'am.
you so this is not, so then if we then the union of this is not a1 union a4, right? So this won't be the minimum number, right?
Yes, ma'am. Oh, that's why I confuse, ma'am.
Has, so this is not the answer then, right?
Yes, ma'am.
So for this it should be 3. If will 3 also work, let's see. If n equal to 4, uh, okay,
Suppose if you take, ma'am,
yeah,
selling, if n or k is even number, then can we write selling function n upon k plus 1,
okay, let's see, like you are saying ceiling function, n
n
k
upon k plus
plus
1,
1,
1
okay.
for n or k even number.
hmm, I'm not sure, wait, like, let me see. So if even if, like, if here we are considering three sets, suppose a1 a2, okay, 3 a1 a2, so yeah, so if we have, so suppose let's try to do it for 2 first. So is this fine? If for 2 is it fine? Let's see, for k equal to 2, is this answer fine? So you have n choose 2 plus 1 and you want to use pigeonhole principle, right?
Yes, ma'am.
So for pigeonhole, what can you take you as your holes? So okay. Hmm. So for this, it 3 is fine, I guess. For this, 3 is fine, because why 3 is fine? E1, E2. Okay, yeah. So this is the question. I can't, I can't like think of an argument why is this true right now. Okay. So do you have a, like, why did you think that ceiling function should be the, like, this should be the answer? They like,
For ma'am, we
hmm,
are taking for
hmm.
if n is odd number, that we can't take na decimal number, na ma'am.
Yeah. That is fine. That is fine.
Yes, ma'am.
But why the ceiling function of n over 2 only, right? N over k. So you are saying, okay, you are basically dividing it to k set. So I think it, like, I don't think it should be always true. Like, let's say for bigger things, if we are saying and k equal to 3. So if you are saying k equal to 2, suppose, yeah, uh, is it fine then? K equal to 2, then the ceiling function will give you 4, right?
Yes,
Your,
ma'am. Yes, ma'am.
if k equal to 2, and then, so see, then also it won't be fine. We can take another like this, a1 a3, then also this is not fine. See, so
Yeah, ma'am. If
for this, so this is not fine. This the n over 2 by plus 1, this is, even if we add plus 1, then also this is not the answer, right? See, like, you have the, do you understand, we have this counter example. So
yes,
for this and this, for n equal to 6 and k equal to 2, this term is coming out to be 4, and we can take our collection to be this. And so, hmm.
Ma'am, this four now. Then we are taking already four collection now.
Yeah. So, but the union, so this, so according to this, your answer should come out to be 4, right? According to
Yes.
this form, the one you are saying, the n over k, ceiling of n over k plus 1 for nke1, right?
Yes, ma'am.
But so if it is coming out to be 4, if we take this collection, this is two element subset and these are four sets, but their union is not this whole set, right? So this is not.
If you if you take another mem collection, suppose A1, A2, A3, A4, A1, A2, A2, A3, A3, A4, and A
Yeah,
like
yeah, if we
this.
take another collection then it is fine. uh
Yes.
but I think like the, so see, but the question is find minimum number of collection of subset whose union will be A. So I think what the question is asking is that this, if you get this number M, if your answer is M, if your answer is M,
Yes.
then if you pick any M collection, any collection, their union should
Yes.
turn out to be the whole set.
Yeah.
So
I
is
think
this
this is
question like, where did you see this question? Like, do you have this proper statement or uh, this is the question? This is the statement, right?
yes, ma'am.
Hmm. Was it like what?
Actually,
Yeah. What were you saying? Yeah.
you continue, ma'am. No.
No, no, it's okay. Uh, okay. What you can do, like, do you, if so where did you see this question from, like?
I have made this question, ma'am.
Oh, you have made this question, okay.
Yes.
uh
Actually, ma'am, I am doing
hmm,
PhD from NIT Arunachal Pradesh in
okay,
mathematics.
yeah, yeah,
So,
okay,
and my area is combinatorics.
okay, okay, okay. Okay, so like, okay, so like, okay, so the okay, fine, then we can, maybe you can like put it up in forum. Okay, you like put the precise question in forum, I'll look at it, and if I have some thoughts about it, I'll discuss it in the next session. Is that fine?
Okay, ma'am.
Will you put this in forum, the question?
Otherwise, ma'am,
Yeah.
yes, ma'am.
Huh?
Otherwise, ma'am, if you free in any day, then you can contact me on email, ma'am. I
Okay,
want to discuss about this question.
okay, okay,
If
yeah,
you feel free,
okay, yeah. So, yeah, okay, then you, uh, yeah, so this is my email ID, you can contact me. Okay.
okay, ma'am. Send me in chat, ma'am.
Okay, yeah. uh,
Ma'am, can I ask you are from which institute?
okay, I am doing PhD at Aisar Mohali. Aisar Mohali.
Okay, ma'am.
Yeah.
One friend, one my junior is was doing Azar Mohali PhD, but right now he left, I think,
Okay, okay.
in
Oh,
mathematics background.
okay. Okay, that's okay. Like, okay, then I'll continue with the problem that we were doing before. Okay, fine. Uh, so we were in the second question. We were in this question.
Sorry, ma'am. Sorry for interrupt.
Haha, no, it's okay. No, it's okay. Yeah.
Okay,
So
ma'am.
also, like, okay, so how is the course, like, how, like, do you have, is the course going fine for you? So we have these now we have these vertices. Okay. Okay, okay, cool. Then it's fine. Yeah. Sorry for the interruption. So we were discussing this question. We are trying to calculate. So for this question, what we are doing, we are trying to find the inequivalent coloring of this graph uh, where the set is edges and the group G is the automorphism of H. So what I was saying, that if you want to construct a graph automorphism, and this is the graph, so graph automorphism preserves degree. So we can see the degree of V1 is 3, degree of V2 is 4, V3 is 5, and rest all the vertices are 1. Rest all the vertices have degree, all the vertices have degree 1. So now if you want to construct the graph automorphism, so V1, V2 and V3, these vertices should be fixed, because there is no other so because degree 3 vertex under graph automorphism should go to degree 3 vertex, but there is no other degree 3 vertex other than vertex 1, and similarly for V2, V3. So therefore we get that under H, under graph automorphism, V1, V2 and V3 are fixed. So only vertices that are allowed to be changed are V4, V5, V6, V7, V8. But here also we have another condition. We have these first three, so these vertices which are lying on the triangle are fixed. Now the another condition on the graph automorphism is that if 3, 4 is an edge, so we see that vertex 3 and vertex 4 are making an edge, then the images of these vertices should be an edge too. So V1, V2, so we can see that only this 4, 5, 6, these are allowed to go to, so 4, 5, 6 can only go to each other. These three vertices should go to each, like these three vertices should permute among themselves, and these two vertices should permute among themselves. 4 can't go to 7, 4 can't go to 8, because if 4 is going to 7, but this 2 and 3 are fixed. So 3, 4 will be an edge, but we don't have an edge going from 3 to 7 or 8. So we see that 4, 5, 6 should be permuted among themselves, and 7, 8 should be permuting among themselves. So we see the H is basically permutation on 4, 5, 6 cross permutation on 7, 8. So order H will be, so this is S3, it has order how much? 3 factorial, and this has order 2 factorial. So order H is 2 factorial. So order H is 3 factorial into 2 factorial, which is 24. And now let's list down all the permutation. So we have 1, 2, 3 is fixed in all the permutations. So we want to so is it fine? 3, sorry, this is 12. 3 factorial into 2 factorial is 12. So now we want to list down all the automorphisms of H. So from our previous discussion, 1, 2, 3 is fixed, but 4, 5, 6 are allowed to permute among themselves, and 7, 8 are allowed to permute themselves. So among 7, 8, we have 2 permutation. Either 7 and 8 are fixed, which is the identity permutation on 7, 8, or we are swapping 7, 8. So we see, so let's first take the case when 7, 8 are swapped. And now then we have, we can list down all the permutations on 4, 5, 6. So we have that this is the group of permutation. 4, 5, 6, this is same. 4, 5, 4, 6. 4, 5, 4, 6, then 4, 6, 5, and the identity. So these are the how many are they? 1, 2, 3, 4, 5. I am missing one more, which is 5, 6. So we see These are the these permutations, and we can have the same case. So we have these 6 permutations, and other 6 come from when 7 8 is fixed. So we have all these things, but 7 8 is fixed. So in this manner we get our 12 permutations. And now we apply the application to Burnside lemma. And if we want to calculate the G inequivalent curl ring, it is basically 1 over order G, sigma pi belongs to G, and n C pi. So here we are counting over all the permutations of G, and C pi is the number of cycles. So we see order G was 12. Now number of cycles in this permutations are 1 2 3 4 5. So it has 5 cycles. This permutations have 6 cycles. This permutation also have 6 cycles. Okay, no, this one has 1 2 3 4 5 cycles, right? And this has 1 2 3 4 5 6 7. So 4 5 6 7, and this has 6 cycles. And now here we'll have in this 7 8 is also getting distributed in 2 cycles. So this will have 6 cycles, this will have 7 cycle, this will have 7 cycle, this will have 6 cycle, this will have 8, and this will have 7. So now we see that 1 over order 12. So how many permutations have 5 cycles? 1 2 permutations have 5 cycles, and we have 3 number of colors is 3. So it is 2 into 3 5. Now how many permutations have 6 cycle? 1 2 3 4 5. So 5 into 3 6, plus how many permutations have 7 cycles? 1 2 3 4. So 4 into 3 to the power 7. Now 6 cycles, 1 2 3 4 5, plus 5 into 3 to the power. Okay, wait. So we have counted 5 cycles, we have counted 6 cycles, we have counted 7 cycles. Now only 8 cycle one is left, which is 3 raised to the power 8. 1 5 10. So we see this is the answer. So how are we getting this? Basically in this if we have to find the inequivalent curl ring, what we do, we first list down all the permutations which are there in group G. Then we express them as a product of disjoint cycles, and then we count the number of disjoint cycles. And then the final answer is 1 over order G. Then we sum it over n raised to the power C pi, where C pi is the number of cycles. So this is what I have done, and we get this is the answer. Now, next question is we have to provide transport functions, generating series, and type generating series for the species below. So first of all, let's recall what are species. So species F is a rule that assigns, so it is a rule which is assigning a finite set Fu for each finite set U. So it can be considered a rule which is assigning a finite set to each finite set. And if we have a bijection between any two finite sets, so we have these finite set U and V, and if we have a bijection, then this species F, it is also assigning a map F sigma from Fu to Fv, and this rule should satisfy these following condition. That so we have this identity bijection. So if we have a set U, we have this identity transformation which is a bijection. So this rule should send identity of U to identity of Fu. And similarly, if we have two bijections, sigma and tau, tau is a bijection from U to V and V is a bijection from sigma to W, then sigma composed with tau is a bijection from U to W. So So this rule this rule should send sigma composed with tau to f sigma composed with f tau. So, and this f sigma are what is called as transport functions, and then it is easy to see that these transport functions will also turn out to be the bijection. So what is species doing? We are assigning a set to each finite set, and we are assigning a bijection to any bijection between finite set. Now generating series for a species f is defined as follow. First of all, we define fn to be the order of the set which is assigned to the n element set. So f is a function which is assigning a set to each finite set. So fn is the set assigned to any n element ordered set, and generating series of f is given by this, where it is given by fn into x raised to the power n by n factorial. N factorial. So coefficient of x raised to the power n by n factorial, what is the coefficient? It is the number of f structures on a set of order n. Now so any element of fu, to each u we are assigning a set fu. Any element of fu is called a f structure on u. Now we also have a relation on these f structure. So if we have two s structures, say s and t, we say that these two f structures are isomorphic if we can find a bijection in u which is sending this first s structure s to u. So this, and we can see that this relation is an isomorphic, is an equivalence relation. So then we further define tf u to be the equivalence classes of these f structure, and the relation is given by the isomorphic relation, and fn tilde is the order of these equivalence classes of u, where u is an n element order set, and generating series of f is given by sigma n raised to the power 0, where the coefficient of x raised to the power n is fn tilde. So fn tilde is basically counting f structures on n element set up to isomorphism. So now we are given some species, so let's do once, and second we'll leave as an exercise. So we have to provide transport function, generating series, and type generating series for the species below. So we have this species, first we have this species power set of x, APL. So what is a species? It is a rule which is, so if u is any finite set, it is assigning a finite set to each u. So what is pxu? So since it is a power set of x, pxu is the collection of all subsets of u, A, such that A is a subset of u. And we know that order of px. So if the order of u is n, then power set is the collection of all the subsets of u, and we know that the number of subsets of u is nothing but 2 raised to the power order u. So now to give a rule, first we have this. Now if we want to define a transport function for px, so for px we have to give, so given any bijection f from u to v, transport function is basically we have to define, if we have a bijection from FU, then we have to define a map PXF from power set of U to power set of V. So any so basically we have a bijection from U to V. So now we have to, using that bijection, we have to say we have to set up a bijection between power set of U and power set of V. So since we have a bijection, what we know that order of U should be equal to order of V. So here it means bijection is basically meaning that we are just relabeling the elements of U. So if we have U1 UN and V is V1 Vn, so this power transport function is simply we are sending some A, which is suppose UI1 UIK, we are sending this to FUI1 FUI2 FUIK. So now if order of U is equal to n, what is the order of PU? We just discussed, it is 2 raised to the power n. So we see that Fn is equal to 2 raised to the power n for all n. So generating series for this will be sigma. So Fn is the coefficient of this, 2n xn n factorial n greater than equal to 0, which is further we can simplify as, and we see that it is nothing but e to raised to the power 2x. So this is the generating series. Now we also have to find the type generating series. Type generating series, that means that we have, suppose my set U is A1 AN. So PU is the collection of subsets of U. Now, so any P structure on U, is a subset of U, and we say that suppose if A, B are two subsets of U, so we'll say A will be related to B if and only if we can find a function bijective function, say alpha from U to U, such that P alpha sends A to B, and this is easy to check. So since any function here, so if we have these vertices, any bijection here is basically we are relabeling the elements of U. So when two subsets should be isomorphic, when will we be able to construct a bijection which will send a subset A to B? A will be related to B if and only if order A is equal to order B. Because we can, so if A, suppose if A was, our U is U1 UN and A is a subset of U, which is say UI1, UIK, and B is the same B is the K, another K element subset, say UJ1, UJ2, UJK. Now we are saying that A is related to B. So what we should, if we are saying A is related to B, we should be able to construct a bijection from U, which is sending A to B. So we want A to go to B. So what is the natural bijection that we should construct? We should construct alpha U from U as follows. Alpha U I1 is equal to UJ1. Alpha UI2 should be UJ2. And similarly, alpha UIK should be UJK, and extend it to rest of the elements. So we'll see that if this is this, then P alpha A is what? Alpha UI1, alpha UI2, and alpha UIK, which is by definition we have defined it to be UJ1, UJK. So we see that any two sets which have same order are isomorphic. So now if we want to construct so what are the number of isomorphic classes? So two sets are isomorphic if and only if they have same order. So if U has order n, what are the possible orders of subsets? Possible orders of subsets are number of isomorphic classes is equal to number of possible orders of subsets of S, subsets of U, and possible orders of U if order U is n are either it has no element. Yeah.
Are you writing down something? Because actually I'm just seeing a static page of where you just explain the graph automorphisms and nothing else. I mean, you are just explaining this since long, but there is only static page. I mean, nothing you know what you're explaining actually.
Okay. Yes, I was explaining something. So you are not able to see it. You're saying
there is actually the display image only saying a static page where you explain the graph automorphism, and this I think first slide only.
Oh, I see. Okay.
I'm actually doing two parallel classes simultaneously, so sorry for that.
Sorry, I didn't. What are you saying? Yeah.
I'm actually taking two classes simultaneously in parallel. So.
Oh, okay.
But I just noticed that your slide is not changing. I mean, whatever you're writing is not shown visible.
Okay,
here.
okay, yeah. Now is it visible, right?
Yeah. Now it's visible.
So we see. So I was saying that. So possible orders are 1 till 1 to n plus 1 till n. So we see that we'll have n plus 1 isomorphic classes. So type generating series will be, so if we have n element order set, we have n plus, so f tilde n is coming out to be n plus 1. So it is n plus 1 raised to the power x raised to the power n. So this is the answer. Similarly, you can do the B part, try to construct first the transport function, then generating series, and then type generating series. Okay, this was all for today. If you have any questions, you can ask. Okay then.